Welcome to G Fun Facts Online. Today, we are embarking on a journey across time and space to solve one of the greatest riddles in the solar system. We are going to Mars, but not the dusty, rust-colored desert we see in our telescopes today. We are going back 3.6 billion years to a time when the red planet was seemingly at war with its own physics. There is a paradox that has haunted planetary scientists for decades, a contradiction written in stone and sand that just does not make sense. Here is the problem. When we look at the geological record of ancient Mars, the planet screams wet. We see river channels carved into rock, ancient lake beds, and sedimentation that implies standing water for millions of years. But when we run the climate models based on what we know about the universe, the physics whisper cold. The math suggests Mars should have been a frozen wasteland. For years, this disconnect suggested that either our understanding of ancient Mars was fundamentally flawed, or we were missing a massive piece of the puzzle. But now, a groundbreaking convergence of new climate simulations and geological analysis has offered a solution, and it changes everything we thought we knew about habitability. It turns out Mars might have been a frozen world after all, but one that harbored a secret. Beneath a protective veneer of seasonal ice, and fed by a vast, pulsating network of underground aquifers, ancient Martian lakes did not just survive the deep freeze, they thrived. Let us break down the magnitude of this discovery. To understand why this is such a huge deal, we have to look at the solar system as it existed during the Noachian and early Hesperian periods. These are the eras when the most dramatic water features on Mars were formed. But there is a catch. Back then, 3.6 billion years ago, our sun was not the bright furnace it is today. It was a faint young sun, roughly 30% dimmer. Now, consider the geography. Mars is positioned 140 million miles further out from the sun than Earth is. In such feeble light under a dim star, Mars should have been locked in a permanent, unyielding ice age. Dr. Eleanor Moreland, a lead researcher at Rice University, whose team recently published these findings in AGU Advances, puts it quite bluntly. She notes that if you run a standard climate model for early Mars, the numbers just do not add up for liquid water. The average global temperature would have been well below freezing. It is a mathematical impossibility under standard conditions. Yet, the reality on the ground tells a different story. The Curiosity rover is currently rolling over mudstones in Gale Crater that are undeniable proof of a calm, long-standing lake. This is the faint young sun paradox. How do you get a lake on a planet that should be a popsicle? In the past, scientists tried to force the models to work. They hypothesized that maybe ancient Mars had a massive atmosphere, injected with greenhouse gases like carbon dioxide and hydrogen, effectively terraforming itself to be warm and wet like Earth. But those scenarios have always been shaky. They require atmospheric conditions that are chemically unstable or incredibly difficult to sustain for the millions of years required to form the geology we see. The new consensus, however, stops trying to turn Mars into a tropical paradise. Driven by sophisticated proxy system modeling, the new theory suggests we do not need a warm Mars. We just need to understand the physics of ice. The breakthrough came when researchers at Rice University and their colleagues stopped trying to melt the entire planet. Instead, they focused on how specific bodies of water behave in cold climates. The team adapted a climate model originally designed for Earth, one used to reconstruct ancient climates from tree rings and ice cores, and they re-engineered it for the Martian environment. They fed it data derived directly from the sediment layers of Gale Crater, treating the rocks themselves as a climate archive. The simulations revealed a startlingly resilient mechanism, something known as the thin ice solution. In this scenario, ancient Martian lakes were not open bodies of shimmering blue water under a sunny sky. Instead, they were capped by a layer of ice, perhaps only a few meters thick. Now, you might think ice would kill the lake, but the model shows that the ice did not crush the lake, it saved it. Dr. Sylvia D., a climate modeler and co-author of the study, explains that a thin layer of seasonal ice acts like a thermal blanket. It creates a decoupling effect. It separates the liquid water below from the freezing atmosphere above. This is crucial because evaporation is a huge source of heat loss. By capping the lake, you stop evaporation. But because the ice is thin and clear enough, it still allows sunlight to penetrate during the summer months. This creates a greenhouse effect inside the lake itself. The model showed that even if the air temperature outside hovered at -10 degrees Celsius or 14 degrees Fahrenheit, the water beneath the ice could remain liquid, hovering just above the freezing point. These conditions could stabilize a lake for decades, centuries, or even longer, without requiring a dense, heat-trapping atmosphere that the physics suggests Mars never had. But a thermal blanket is only half the story. A blanket keeps heat in, but it does not generate heat, and it does not create water. If Mars was so cold, where did the water come from to fill these lakes in the first place? It was not rain, and it was not snowmelt, which would have been scarce. This is where the story shifts from the surface to the deep subsurface. We have to talk about Martian aquifers. The title of aquifer on Mars is not a misnomer. It is the central artery of the planet's hydrological system. Recent geological studies, including incredible data from the European Space Agency's Mars Express orbiter, have identified the fingerprints of a planet-wide groundwater system that once spanned the Martian globe. This changes our visual model of a Martian lake completely. In crater lakes like Gale and Jezero, where the Perseverance rover is currently exploring, the water was being pushed up from below. Dr. Francesco Salese, a geologist who has mapped these ancient basins, uses a great analogy. He says we should not think of these lakes as swimming pools being filled by a hose from above. We should think of them as windows into a massive underground water table. The pressure from the global aquifers would force groundwater up into deep crater basins. And crucially, this water was likely warmer than the surface. It was being heated by the planet's internal geothermal gradient. So we arrive at what we can call the sandwich model for Martian habitability. Imagine this three-layer system. On top, you have the thin, seasonal ice cap that seals the system and traps solar heat. In the middle, you have the liquid water, rich in dissolved minerals. And at the bottom, you have the connection to the warm, mineral-rich aquifers that constantly replenish the lake. This interaction is absolutely vital. If these lakes were just isolated puddles on the surface, they would have eventually frozen solid or sublimated away into the thin air. The connection to the aquifers meant they were part of a living, circulating planetary system. The groundwater influx helped regulate the temperature, and perhaps more importantly, the chemistry of the lakes. It prevented them from becoming too salty or too stagnant to support chemistry. But do we have proof? Is this just a computer simulation, or is it real? The proof lies in the mud. The Curiosity rover has spent over a decade climbing Mount Sharp in Gale Crater, analyzing layer after layer of sedimentary rock. What it found was puzzling under the old warm and wet dichotomy, but it makes perfect sense under the cold and wet model. Curiosity found mudstones. These are fine-grained sedimentary rocks formed by silt, settling at the bottom of a calm body of water. But crucially, these layers show no evidence of the massive, chaotic ice wedges or glacial scarring that one would expect from a lake that froze solid to the bottom. Dr. Moreland points out that the sediment layers in Gale are remarkably orderly. If you had a lake that was freezing solid every winter and thawing every summer, you would see a process called cryoturbation. This is a churning of the soil that disrupts the rock layers. But we do not see that. We see fine, undisturbed lamination. That tells us the water at the bottom stayed liquid and calm, year-round, protected by that ice lid. Furthermore, the mineralogy supports the cold model. Curiosity has detected magnetite and certain clay minerals that suggest formation in water that was cool but not frozen, and chemically neutral. These are conditions perfectly maintained by a groundwater-fed, ice-covered lake. The implications of this model extend far beyond Gale Crater. It forces a reevaluation of the entire Martian landscape. For example, in the southern highlands, researchers have identified vast networks of valleys that seem to start abruptly. They emerge from the ground rather than collecting from wide catchment areas like rivers on Earth do. These are called sapping valleys. They form when groundwater seeps out of an aquifer and erodes the earth away, causing the ground to collapse into a channel. This aligns perfectly with the aquifer theory. During the Hesperian period, as the surface cooled and the atmosphere thinned, the water table may have remained liquid deep underground. Occasionally, this pressurized water would breach the surface, creating transient lakes and rivers that would quickly freeze over, preserving their liquid flow beneath the ice crust. And here is a chilling thought. Even today, this system might not be entirely dead. Radar data from the south pole of Mars has hinted at the presence of liquid water, or perhaps a briny slush, buried a mile beneath the ice caps. These could be the last remnants of the great Martian aquifers, retreating into the deep dark as the planet died. So, what does this mean for life? For astrobiologists, the shift from a tropical Mars theory to a frozen aquifer Mars theory is not a disappointment. In fact, it is an incredibly exciting pivot. On Earth, some of the most stable and long-lived ecosystems are found in subglacial lakes, like Lake Vostok in Antarctica, or in the deep groundwater of the crust. These environments are protected from surface radiation, they are stable in temperature, and they are rich in chemical energy. This is perfect for microbial life. If ancient Martian lakes were covered by ice, that ice would have acted as a shield. It would have protected potential life from the harsh ultraviolet radiation of the young sun, which Mars' thinning atmosphere could no longer block. The connection to aquifers would have provided a steady supply of dissolved ions, which is essentially food for chemotrophic bacteria. Dr. D notes that we should not be looking for Martian coral reefs. We should be looking for the kind of slow, hardy life that thrives in the dark, cold waters of Earth's cryosphere. The thin ice model suggests these habitats could have existed for millions of years, long enough for life to potentially gain a foothold. As the Perseverance rover collects its samples in Jezero Crater, samples that are destined to return to Earth in the 2030s, Scientists are now looking for specific signatures predicted by this new model. They are hunting for dropstones, which are rocks dropped into fine mud by melting ice rafts floating above. They are also looking for specific isotopic ratios in oxygen that would confirm the presence of an ancient ice cover. The concept of Martian aquifers and frozen lakes are no longer competing theories. They are two halves of the same hydrological engine. It was an engine that allowed a dying, freezing planet to hold onto its lifeblood for millions of years longer than anyone thought possible. Mars, it seems, was not a failed Earth. It was a successful icy world, hiding its secrets beneath a glass-like shell, waiting for us to crack the code. That is the story of the thin ice and the deep water, and it is a story that is only just beginning to be read. Thank you for listening to G Fun Facts Online.